Hi, good morning everyone. Myself Dr. Imanshu Goyal and I will be discussing today the theory of games. We have already discussed the pure strategy. We'll be now discussing about the mixed strategy games. So mixed strategy games are basically primarily those games we don't have a settle point. So the settle point we have already discussed in the previous lecture. So you can go to that lecture and have a look at what is the saddle point and how do we calculate the saddle point. So when there is no saddle point, a mixed strategy game is adopted by the players, right? In what do you understand by a mixed strategy? We have already discussed that, right? So we'll be discussing now that how mixed strategy is applicable to that particular problem, right? It is not necessary that there is always a settle point exists. Therefore, we use the mixed strategy game. In such cases, to solve games, both players must determine an optimal mixture of strategies to find a settle point. Therefore, in order to find the settle point, the players have to adopt an optimal mix of strategies. The optimal strategy mixture for each player may be determined by assigning to each strategy its probability of being chosen. The strategies so determined are called mixed strategies because they are probabilistic combination of available choices of strategies. Uh, this is how a mathematical notation I would say of mixed strategy games. The value of game obtained by use of mixed strategy represents which least player A can expect to win and the least which player can be lose. The expected payoff matrix to a player in a game with arbitrary payoff matrix Aij, which is denoted by Aij of order m into n. M here stands for the number of rows and n stands for the number of columns, is defined as E P of Q summation I to the m j to the n pi aij and qj, where p and q denote the mixed strategies for players a and b respectively. Here p and q denotes the mixed strategy adopted by the players a and b, and m and n are the number of rows and columns, right? And I and j are the denominations of this cost matrix. So here also the maxim and minimax criterion is applied where we don't have a saddle point. Consider a m into n game without any saddle point. Suppose we are taking a game where who doesn't have a saddle point and it's a payoff matrix of m into n, right? That is strategies are mixed. That means the strategies mixed strategy has to be used. Let player 1 and player 2 PM with the probabilities with each player A will play his moves A1, A2 till AM respectively, and let Q1, Q2 and Qn be the probabilities of which player A will play his moves B1, B2 and Bn respectively. Right. Also P1 plus P2, the probabilities of all the players will be equal to always equal to 1, and Q1, Q2 and Q till Qn is equal to 1. Right. So Pi is greater than equal to 1 and Qj is also equal to greater than equal to 1. The expected payoff function of player for player A is E P Q summation I till M J till N, right? Pi A I J and Qj, right? For a player A, maxi min minimax criterion will be applied. For example, V is the value of the payoff matrix and M max is P and min is Q. So E is the expected outcome, I would say, and P of Q is equal to max, which max of P into a min of J, right? Summation I is equal to till M Pi A I J. So this is some mathematical notation I would say, which is used for calculating the value of the payoff matrix. Here min j pi aij denotes the expected gain to A when B uses his jth strategy. That means if the gain of A is denoted by min of J, and when B uses a jth strategy. For player B, similarly for player B as well, right? And the payoff or probably the expected loss which B will incur because A has gained, right? So I already discussed that A always will always be the gainer and B will always be the loser. When A uses ith strategy, the relationship between V is always less than equal to V bar. V bar here denotes the loss which was incurred by player B, and V here represents the gain incurred by the A, right? Holds good in general, and when Pi and Qj correspond to the optimal strategies, the relation holds in equality sense, and the expected value for both the players becomes equal to the optimum expected value of the game, right? For any game which is a 2 by 2 two-person zero sum game, I would say, without any settle point, having the payoff matrix for player A and player B, the optimum strategies will be SA is equal to A1 A2 P1 P2, and SB is equal to P1 B2 and Q1 Q2, and determined by P1 is equal to A22 minus A21 upon my A11 minus A12. That means the later has to be subtracted from the former, right? Q1 is equal to A22 minus A21, and upon may divided by A11 and minus A12. This is also where there is no settle point and it's a two-person zero-sum game. So the mixed strategy will be used here also, where P1 plus P2 is always equal to 1 and Q1 Q2 is always equal to 1. The value of the game. Then how would you find the value of the game, which is the ultimate objective of going through this game theory, is A11 A22 minus A21 A12 upon me A11 plus A22 minus A12 plus A21, right? So this is the formula, or this is the method from which you can find the value of the game A. I've quoted here one example for you to understand much better. So the example says that there is a payoff matrix which is given for player A and player B, and the payoff matrix is 5 1 3 4, right? So for SA, man, that means the strategy for SA for the player 1, I would say, will be A1 A2 P1 P2, and SB is B1 B2 and Q1 Q2. We knew that P1 P2 is equal to 1 and P1 Q1 plus Q2 is equal to 1. If E denotes the expected payoff function, then EPQ, how would you find the EPQ, right? The formula will be like this: 5P1 Q1 plus 3 1 minus P1 into my Q1 plus 1 into P1 minus 1 minus Q1 plus 4 into 1 minus P1 into my 1 minus Q1 is equal to 5P1 Q1 minus 3P1 minus Q1 plus 4, right? 5 into my P1 minus 1 by 5 upon my Q1 minus 3 by 5 plus 17 by 5. This is how we solve. If we we substitute P1 is equal to 1 by 5, it ensures that his expected ratio or expectation n is at least 17 by 5. That means if P1 is 1 by 5, then n will be at least 17 by 5, right? I can't be sure of more than 17 by 5 because Q1 is equal to 3 by 5. We can keep EP1 Q1 down to 17 by 5. Hence, the optimum strategy for A and B are A1 A2 1 upon 5 4 by 5, and B1 B2 3 by 5 and 2 by 5, and the value of the game will be 17 by 5, which we have calculated using the above formula. So I guess that's it for today. Thank you.